This is the fourth section of chapter 5 on dynamics, and this section is on horizontal oscillation. Now, we have horizontal oscillation for springs and strings. They're both slightly different, so we're going to look at both of the cases separately. So starting with springs, here I've got a spring here that's been extended beyond its natural length, so the spring has been stretched. That means that there's tension pointing back towards the spring. It wants to get back to its natural length, and the acceleration is going to be pointing in the opposite direction over here because we have simple harmonic motion. I'll explain that in a moment. So we've got this stretching beyond its natural length. It sort of pulls the mass back towards its natural length, and incidentally at the natural length, which is actually going to be the center of oscillation, we get the maximum velocity and acceleration of 0, and then it continues in simple harmonic motion, and it's actually going to be compressed by the same length on the other side of its natural length. Then we have thrust in the spring, it's going to push it back, so the mass is going to be oscillating like this. Yeah, obviously I can't show the change in velocity that well, but it's going to be moving between an extension of x to a compression of x. So let's go through some of these things here. So first of all, the spring extends and compresses, so there's going to be no slacking with the spring, and we'll talk about how that is different with a string in a moment. The initial extension or compression is equal to the amplitude of simple harmonic motion, so which we spoke about. So an extension of, let's say, 2 meters will mean an amplitude of simple harmonic motion of 2 meters. So that initial extension compression is equal to the amplitude of simple harmonic motion. Oscillation about L, so this is going to be the center of oscillation, the natural length, continues at the same amplitude. So there is no damping, so that amplitude remains the same. Now, if we had friction, for example, then we'd expect that oscillation to decrease until the mass stays at its natural length. But we are simplifying the case, and it's going to be continuing at the same amplitude, so there's no damping with this simple harmonic motion. And I've got down here the equations we're going to be using. This is the only one that we haven't used, I think, previously, is Hooke's law to work out the tensional thrust in the spring. And I think that's it. Yes, if we need to show simple harmonic motion, then we need to show that our equation for acceleration can be written in this form. Okay, let's move on to the strings. Right, let's move on then and have a look at our diagram here. And you can see it's a different type of diagram to the spring, which oscillated around its natural length. Here, we're going to have a situation where the string goes slack. So let's say, for example, the mass is pulled beyond its natural length here. Then we're going to have tension, pulling back, and then when the string reaches its natural length, the string is going to go slack. So for this section in the middle, there's no harmonic motion. The particle, or the mass, is going to be moving at a constant speed, and that's going to be the speed it was when it was at this natural length here. And then it's going to continue at its natural length, or constant speed, until it moves across, and then it hits its natural length again, and then we get extension, and we get tension pulling back, and we get simple harmonic motion again on this side. And then the mass is going to pull back, it's going to get to its natural length, it's going to go slack again, and then we get constant speed in the middle. So you can see from this diagram that we only have simple harmonic motion at these two ends here when the string is at and beyond its natural length. So we're going to have a motion which is sort of, let's say it starts here, so then it's going to speed up until it gets to this point, and it's going to carry on at that constant speed. And then over here, what's going to happen, it's going to slow down until the velocity becomes 0, and then we get simple harmonic motion from this point up to here, and then simple harmonic motion here, and then it stops, constant speed, and then simple harmonic motion takes over till we get to this point and back again. Okay, so what we have actually is like 2 half cycles of harmonic motion. So we've got one that sort of goes that way, and we've got one that goes in the opposite direction over here. So we've got these 2 half cycles of harmonic motion on either side with this constant speed in the middle. So the string extends only, there's no compression in the string goes slack. When it is shorter than its natural length, so that's going to happen here in the middle section, the initial extension is equal to the amplitude of the simple harmonic motion, just like we have in the spring, but the simple harmonic motion only takes place at the ends. And then when the string goes slack, the speed is constant, and that speed is going to be the speed at which the mass was moving when it hit its natural length. And we use the same equations as we do for spring. So you can see that there are some slight differences. So there are going to be some slight differences to the way that we approach these 2 slightly different types of question. And just like we made a simplification and say there was no damping with the spring oscillation, there's going to be no damping for the oscillation part, the simple harmonic motion part of the string. So the amplitude at these 2 ends we're going to say is the same. So if I've got an amplitude, an extension of 2 meters, then it's going to be 2 meters over here, and we get back 2 meters again over here, and so on. So there's no damping. It continues with the same amplitude at the 2 endpoints. Example 15. A particle P of mass 0.6 kg rests on a smooth horizontal floor attached to one end of a light elastic string of natural length 0.8 meters and modulus of elasticity 16 newtons. The other end of the string is fixed to a point A on the floor. The particle is pulled away from A until AP measures 1.2 meters and released. Right, so let's start with our diagram before we dive into these questions here. Right, so here's my diagram here. I've put on the amount of extension that we have, the mass of the particle, and the direction which the forces are moving in. So remember, this is a string here. This is the point that the string is connected to. So we know when it gets to this length here, it's going to go slack, and then it's going to move across to the other side. So we'll take that into consideration. So part A, it says show that while the string remains taut, particle P moves with simple harmonic motion. Now if we're going to do that, then we need to use in our working an extension of x, not of 0.4. We want to show for a general case of an extension of x that we have simple harmonic motion. So we don't use a 0.4 because that's a particular case. We want to show for a general case. So we start with F is equal to MA. Now we write that as F is equal to M times the acceleration, which is x written with 2 dots. And we'll take the direction to the left. So we're going to take that direction as our positive direction because that is the direction which the tension is pointing in. That's going to be the only force acting on it. So we'll write T is equal to, now we'll put the mass in, 0.6. Now the acceleration we can see is pointing in the opposite direction. So that's going to be negative x double dot there. And we want to work out what the tension is. So we'll use Hooke's law, lambda x over L. Lambda is 16. Remember, we're using the extension of x, not of 0.4. We want to show in a general case, and length of 0.8. So if we simplify that, 16 divided by 0.8 is 20. So we have 20x. So that can now be put into my equation. So I have tension 20x is equal to negative 0.6 times my acceleration, and rearrange it to see if I've got simple harmonic motion. So that means dividing both sides by negative 0.6. So that will give me negative 100 over 3x. So now we can say that since the equation is in the correct form, so the acceleration equals negative omega squared x, p moves with simple harmonic motion, where omega squared is 100 over 3. Moving on to part B, calculate the speed of p when the string returns to its natural length. Well, anytime you see a question that's asking for speed, we're going to be using this equation here. So we need to know omega, or omega squared, amplitude, so we can square it, and extension. So the first thing is we know what omega squared is. We just said it's 100 over 3. The amplitude, well, I said from the introduction that the amplitude is always equal to the initial extension. So that is A is 0.4. And since we're finding the speed when it returns to its natural length, there is no extension. So x is 0. So we'll substitute those in. So with those values substituted in, we get v squared is equal to 100 over 3 times by 0.4 squared amplitude squared minus extension squared, 0 squared. That gives us v squared is 16 over 3. So that means that the velocity, and that's going to be in meters per second, is equal to 4 over root 3. Now, I've not used g, so it's fine for me to leave that answer in exact form. You could, if you want, change it to 3 significant figures, but that's fine to leave it in the exact form in this question. Part C, we want to calculate the time that elapses between the point where the string becomes slack and a point where it next becomes taut. So let's look at our diagram and work out when that happens. Okay, so we've got this initial extension, and at this point it reaches its natural length, the string becomes slack, so it now moves at a natural speed. Now it's going to be moving a distance of 0.8, and then it's basically a length of 0, and then it's going to continue for another 0.8 on the other side here before the string reaches its natural length, and then we get simple harmonic motion on the other side. So remember that diagram that we did at the start. The natural length here, and again the natural length here, is when we have this constant speed. So since p is moving at a constant speed during its slack phase, so this 0.8 here and this 0.8 over here, we can use the speed equals distance over time. Now we're trying to find the time that elapses, so we are going to need the distance over the speed. Now the distance is going to be that 0.8 plus another 0.8 on the other side, divided by the speed, and that speed is the speed that p was travelling at when it reached its natural length, which is what we just worked out, wasn't it? Yeah, calculate the speed of p when it returns to its natural length. So that's just the answer from part B. So it's going to be divided by 4 root 3. So that's just going to be 1.6 divided by 4 root 3. Sorry, 4 over root 3. And that gives us an exact answer of 2 root 3 over 5 seconds. Now you may prefer to write your answer to 3 significant figures. It's fine to leave it in that form, but if I did press my SD button, I get something like 0.692820.323. So 3 significant figures, I'd round that to 0.693 seconds. So part D, calculate the time taken for the particle returned to its starting point for the first time. So this is its starting point here, and we want to work out the time it takes to move all the way over here and then all the way back to its starting point. So I've sort of tried to draw its lengths in a way as it moves through this sort of cycle. So the first part is when the string is in extension up to its natural length. It's moving with simple harmonic motion. So the length goes from an extension, I suppose this should say L plus 0.4, and I guess that should also be L plus 0.4 but in the other direction. So it starts at this length and then it moves down to a natural length, then we get a constant speed at this point, and then at the other end, when it stretches again, we get simple harmonic motion as it stretches to the end, and then it moves back with simple harmonic motion here, and then it's back at its natural length again. And this section here, it's moving with a constant speed and then back with the extension. If I actually look at these parts here, I've really got a full cycle of simple harmonic motion here, split up into bits. So we have the first quarter of simple harmonic motion, the first cycle, then another quarter, and then back over here, the last quarter. So we've got one full cycle of simple harmonic motion, and we want to work out the time for that. Plus, we've got the time at constant speed, that it moves 1.6 this way, and then 1.6 back that way. Now we know the time it takes to move 1.6 in one direction, so we just double that answer. So our working is going to be 2 lots of the constant velocity or constant speed time, which is this, plus 1 full cycle of simple harmonic motion. So here's that formula. Here 2 times the constant speed phase times 1 cycle of simple harmonic motion. So it's going to be 2 times the 2√3/5 that we got from part C. That's the constant speed phase, but only going in one direction. We need to double it because we're going back in the other direction. Plus 1 cycle of simple harmonic motion, and the formula for that is 2 pi over omega. So the 2 times 2√5 becomes 4√3/5 plus 2 pi over omega. Now we worked out before that omega squared was 100/3, so omega is going to be the square root of 100/3. When we work this out on our calculator, it does not give us an exact answer, but we get 2.47392 and so on. So this one we would need to give to 3 significant figures. So 2.47 seconds is the time that it's going to take for this particle P to return back to its natural length, and that answers to 3 significant figures. I think I mentioned that. Example 16. A particle P of mass 0.8 kg is attached to the ends of 2 identical light elastic springs of natural length 1.6 meters and modulus of elasticity 16 newtons. The 3 ends of the springs are attached to 2 points A and B, which are 4 meters apart on a smooth horizontal surface. The point C lies between A and B, such that ABC is a straight line and AC is 2.4 meters. The particle is held at C and then released from rest. So let's draw our diagram first before we have a look at these parts of the question. So part A, what we need to do is show that the subsequent motion is simple harmonic motion. So I've got my diagram here. I can see that initially that the spring on this side, which I'll call spring AC, is an extension by 0.8 meters. So that's going to be the amplitude of simple harmonic motion when I need it later on. And this one initially is at its natural length. Now I've put 2 tensions on because if we want to show simple harmonic motion, remember we don't use the actual value of the extension, we use the value of x. So it could be that either spring AC or string CB or BC is in extension or compression. So we need to set our equations around that of a general extension of x. Right, so before we go any further, let's put on the acceleration. So assuming that it's initially going to be moving to the left, our acceleration will be to the right, so we'll just put that on there. And when we do these extensions, we need to be careful because these 2 springs have been stretched between a distance of 4 meters. So even if the mass was at the center and this was in equilibrium position and not moving, each of the springs would be 2 meters long. They've already got an extension of 0.2 meters. So I'll just write that down. And if I said 0.2, I actually mean 0.4. So I hope this makes sense that both springs are already in extension of 0.4 meters, since they have been stretched to fill a 4 meter space. It's 4 meters between A and B, and 2 times their natural length, 1.6, is 3.2 meters. And if we take that natural length away from the 4 meters divided by 2, so each spring gets that extension shared, we get 0.4 meters. So when we start with the extension, let's say, of spring AC, it's already got an extension of 0.4, and we're going to call any further extension X. Now if we do the same for the other spring and want to work out the extension of spring BC, it's already in extension of 0.4, but it's going to be a slight compression of that extension of X. So one spring gets stretched more than 0.4 beyond its natural length, whereas the other spring is already stretched 0.4 beyond its natural length, but gets squashed slightly because the other spring is extended. So you can see if one is squashed a bit, the other one stretches, and so on. So if I now take to the right here as positive and write my equations, so I'm now going to be using F equals ma. What I will have is, in terms of my forces, the tension of BC minus the tension of AC. The tension of BC, so I'll write this down. Actually, let's just write this down. Tension BC, instead of my alphabet, BC minus tension AC is equal to MA. Now, using Hock's law, we can find the tension of those springs. So BC is going to be lambda, and lambda is 16. So lambda x, its extension is 0.4 minus x over its natural length, 1.6. So that's tension of BC minus the tension of AC. So same modulus of elasticity, value of lambda. Its extension is 0.4 plus x divided by the natural length of 1.6, and that's going to equal the mass 0.8 times by the acceleration. So we'll tidy this up a bit. So first of all, I'm going to times both sides by 1.6 because I don't really like having that fraction there, and 0.8 times by 1.6 is 1.28. So I've got 1.28 times the acceleration is equal to, so these 1.6's are gone, I'll expand the brackets here. So 16 times by 0.4 is going to give me 6.4 minus 16x, and then the second bracket I will get minus 6.4 and then minus another 16x. That gives me 1.28 times the acceleration is equal to negative 32x. Then divide both sides by 1.28, I get the acceleration equal to negative 25x. Okay, so is it P they call it? Yeah, so P moves with simple harmonic motion. Okay, so it's in the form that we want, where omega squared is equal to 25. So moving on to part B, find the period and amplitude of the motion. Part B, so we know that the period of the motion is 2 pi over omega. So omega squared, we said was 25, so omega is 5. So that's just 2 pi over 5 seconds. And the amplitude of the simple harmonic motion, and that's going to be just 0.4 meters. Now why is it 0.4 and not 0.8? So these springs are already stretched. They cannot compress back to their natural length. The most they can compress back to is going to be a well, they're 2 meters. Okay, so that means that if we sort of work that out from here, then that has to be 0.4 meters in terms of the amplitude. It's only free to move 0.4 meters either side of that equilibrium point in the center. And you can see that here, if we add these two together, that's 2.4 meters. So actually these springs have got almost like a new natural length because they've been stretched to 2 meters. So taking that 2 away from 2.4 leaves us with the 0.4. Slightly different question to what we're used to, because even in equilibrium, as I said, these are stretched beyond their natural length. So it's almost like 2 becomes like the new natural length that we're working with, and we work out the extension from basically that new natural length of 2 meters. And lastly, part C, calculate the maximum speed. Well, the maximum speed occurs when the extension is 0. So v squared is going to be equal to omega squared, which we've worked out as 25. The amplitude 0.4 squared, and as I said, an extension of 0 when we get the maximum speed. So that gives a value of v as the square root of 4, so it's 2 meters per second. So let's just highlight those answers. So there's part C there. Part B, we had the period and the amplitude here, and then part A was that proof. So you should now be able to do exercise 5D on pages 196 to 198 of the Further Mechanics 2 book.